Welcome to the e-lecture session for diploma students. In today's session we are going to see some of the conditions involved in parallel operation of transformers or pairing of transformers. The other requirements for satisfactory parallel operation of transformers are given below. Number 1, the turns ratio and voltage rating should be same. Number 2, the polarities of transformers should be same. Percentage impedance of the transformers should be same, and finally the ratio of resistance to reactance, that is R by X, should be same. If two transformer windings have been connected in star, then the neutral points are connected together as shown in figure 4.20. Then the transformer primary is applied with low voltage. Measure the voltage between each secondary terminal of the first transformer and the second transformer by using a voltmeter. If the polarities are similar, then the voltmeter reading will be 0. Then permanent connections can be made. For example, the voltage between the terminals P, X, Q, Y and R, Z is 0, then connect P and X, Q and Y and finally R and Z. Now we will move on to trial 1. Two similar terminals of the secondaries are linked as shown in figure 4.21. So this is one transformer, this is another transformer to be connected in parallel. Now let me connect this P terminal to the X. Now a low voltage is applied to the primary. Measure the voltage between Q and Y. Similarly, measure the voltage between R and Z. If these voltages are 0, then connect P and X, because already P and X are connected. Only thing which is left over is Q and Y. You connect Q and Y, and similarly you can connect R and Z like this. P and X can be connected, Q and Y can be connected, R and Z can be connected. On the other hand, if the voltage between Q and Y is not 0, then measure the voltage between the terminals Q and Z. So in the previous trial what we have done is we have measured between Q and Y, it is 0, between R and Y we have measured, it is 0. Now on the other hand, in the second case, if the voltage between Q and Y is not 0, then we need to measure between Q and Z. If this voltage is 0, then measure the voltage between R and Y. If this voltage is also 0, then connect P and X, Q and Z, R and Y. So instead of Q and Y I am going to connect Q and Z here, and R and Y I am going to connect. Then trial 2. In the first trial, if the voltage between Q and Y and between Q and Z are not 0, then connect the terminals P and Y as shown in figure 4.22. So I can connect it here, P and Y. Now measure the voltage between Q and X. If it is 0, measure the voltage between R and Z. If this is also 0, then connect the terminals P and Y, Q and X and R and Z. If the voltage between Q and X is not 0, then measure the voltage between Q and Z. If it is 0, then measure the voltage between R and X. If this is also 0, then connect the terminals as usual Py, Qz and Rx. Trial 3. In the second trial, if the voltage between the terminals Q and X and Q and Z are not 0, then change the test connection as shown in figure 4.24, that is connect P and Z. Now measure the voltage between the terminals Q and X. If it is 0, then measure the voltage between R and Y. If it is also 0, then connect the terminals P and Z, Q and X, and similarly R and Y. If the voltage between Q and X is not 0, measure the voltage between Q and Y and similarly R and X. This voltage must be 0. Now, connect the terminals P and Z, Q and Y, and R and X. Load sharing by two transformers connected in parallel with equal voltage ratio. Let us now consider the case of two transformers connected in parallel having equal voltage ratios. The two transformers are having their no load secondary voltages equal. E1 is equal to E2, which is equal to E. These voltages are in phase with each other. This is possible if the magnetizing currents of the two transformers are nearly equal to each other. With this case, the primaries and secondaries of the two transformers can be connected in parallel and no current will circulate under no load condition. This is represented by the figure 4.25, because the no load component connection is not shown here in this equivalent circuit. If magnetizing components are neglected, the two transformers are represented as shown in the figure 4.26. R1 X1 is the impedance of the primary and R2 X2 is the impedance of the secondary. The phasor diagram under this case is shown in 4.27. The two impedances Z1 and Z2 are in parallel. The values of Z1 and Z2 are with respect to the secondary. Z1 and Z2 are in parallel, therefore, the equivalent impedance is given by 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2. So, Z equivalent is equal to Z1 Z2 divided by Z1 plus Z2, as seen from the phasor diagram. I1 Z1 is equal to I2 Z2, which is equal to I Z equivalent. Here I1 is equal to I Z equivalent by Z1, which is equivalent to I Z2 divided by Z1 plus Z2. Then I2 is equal to I Z equivalent by Z1 plus Z2, which is equal to I Z1 divided by Z1 plus Z2. Multiplying both terms of above equation by voltage V2, we have V2 I1 is equal to V2 I Z2, because I am going to substitute this Z equivalent here in this equation. So, V2 I1 is equal to V2 I Z2 divided by Z1 plus Z2. Similarly, V2 I2 is equal to V2 I Z1 divided by Z1 plus Z2. Now, let us move on to the load sharing by two transformers connected in parallel with unequal voltage ratios. Now, we will consider the case of two transformers working in parallel and having unequal voltage ratio. So, this is shown in the diagram. Z1 and Z2 are not equal here. The voltage ratios of the two transformers are not equal. The parallel operation under this case is still possible, but as seen previously, there would be a circulating current under no load condition. Let us consider a voltage ratio of transformer 1 is slightly more than that of transformer 2, so that the induced EMF E1 is greater than E2. Thus, the resultant terminal voltage will be E1 minus E2, which will cause a circulating current under no load condition, that is IC is equal to E1 minus E2 divided by Z1 plus Z2. From the circuit diagram, we have E1 is equal to V2 plus I1 Z1, E2 is equal to V2 plus I2 Z2. Also, IL is equal to I1 plus I2. V2 is equal to IL ZL, which is equal to I1 plus I2 into ZL. E1 is equal to I1 plus I2 into ZL plus I1 Z1. Similarly, E2 is equal to I1 plus I2 ZL plus I2 into Z2. So, these two are the equations A and B. Now, subtracting the equations A and B, we get E1 minus E2 is equal to I1 Z1 minus I2 Z2. So, I1 is equal to E1 minus E2 plus I2 Z2 divided by Z1. Subtracting this value in equation B, we have, so E2 is equal to I2 Z2 plus E1 minus E2 plus I2 Z2 divided by Z1 plus I2 whole bracket into ZL. So, I2 is equal to E2 Z1 minus E1 minus E2 by ZL divided by Z1 Z2 plus ZL into Z1 plus Z2. Similarly, we can find I1 value in terms of E1 and E2. So, it is E1 Z2 plus E1 minus E2 divided by ZL whole divided by Z1 Z2 plus ZL into Z1 plus Z2. Adding the above equations, we can get I1 plus I2 is equal to this expression. Similarly, but IL is equal to I1 plus I2, we know that. So, the load voltage V2 can be calculated as IL into ZL. So, dividing both the numerator and denominator of equation C by Z1 and Z2, we get this expression. So, the adding all the above equations, we get I1 plus I2 is equal to E1 Z2 plus E2 Z1 divided by Z1 plus Z1 Z2 plus ZL into Z1 plus Z2. This is equation C, but we know that total current is equal to I1 plus I2, load voltage V2 is equal to IL ZL. Dividing both numerator and denominator of equation C by Z1 and Z2, we get IL of this expression, that is Z1 E1 by Z1 plus E2 by Z2 whole divided by 1 plus ZL by Z2 plus ZL by Z1. So, similarly, we can write V2 in terms of IL and ZL, which is equal to E1 by Z1 plus E2 by Z2 divided by 1 plus ZL by Z2 plus ZL by Z1 into ZL. So, this is the final expression I1, which is E1 Z2 divided by ZL into Z1 Z1 plus Z2 plus E1 minus E2 by Z1 plus Z2. Similarly, I2 can be derived. So, but we know that E1 minus E2 by Z1 plus Z2 is equal to, that is the core loss component IC. This circulating current IC adds to I1, but subtracts from I2. Hence, the transformer 1 gets overloaded. The transformer will not share the load according to their ratings. If impedances Z1 and Z2 are small in comparison with load impedances ZL, then the product Z1 Z2 may be neglected. So, we get Z1 minus E1 minus E2 divided by Z1 plus Z2 is equal to IC. The circulating current IC adds to I1, but it is subtracted from I2. Hence, the transformer 1 gets overloaded. The transformers will not share the load according to their ratings, and the corresponding phasor diagram is given in 4.29. The two transformers will operate at different power factors. Phi 1 and phi 2 are the power factor angles of these two transformers, whereas phi is the combined phase power factor angle. Here EA and EB have the same phase, but there may be some phase difference between the two due to the possible difference in internal connection as far as the parallel connection of a star star and a star delta 3-phase transformers is concerned. Cooling of transformers. When a transformer supplies a load, two types of losses occur inside the transformer. Number 1, the iron losses. Number 2, the copper loss. The iron losses occur in the core, while copper losses occur in the windings. The power lost due to these losses is dissipated in the form of heat. This heat increases the temperature of the transformer. To keep the temperature rise of the transformer within the limits, it is necessary to dissipate the heat developed to the surroundings. A suitable coolant and cooling method is necessary for each transformer to dissipate the heat effectively to the surroundings. Basically, there are two types of transformers, dry type transformers and oil immersed transformers. In dry type, the heat is taken to the walls of tank and dissipated to the surrounding air through convection. In oil immersed type, the oil is used as a coolant. The entire assembly, including the core and the windings, is kept immersed in a suitable oil. The heat developed is transferred to the walls of the tank by convection through oil, and finally the heat is transferred to the surroundings from the tank walls by radiation. Now, the classification of various cooling methods, they are based on the cooling medium used. Number 2, type of circulation employed. The various coolants used along with their symbols are: for air it is denoted as capital A, gas G, synthetic oil is L, mineral oil O, solid insulation S, and water it is W. There are two types of circulations, which are: number 1, natural circulation, number 2, forced circulation. In natural cooling, the coolant circulating inside the transformer transfers the entire heat to the tank walls, from where it is dissipated to the surroundings, and the transformer gets cooled by natural air. In forced cooling, the coolant circulating inside the transformer gets heated up as it comes in contact with the windings and core. The coolant partly transfers the heat to the tank walls, but mainly coolant is taken to the external heat exchanger, where air or water is used in order to dissipate the heat of the coolant. Various cooling methods or arrangements. Air natural type. This method uses atmospheric air as a cooling medium. The natural air surrounding the tank walls is used to carry away the heat generated by natural convection. It is used for small low voltage transformers. First one is air forced type. In large transformers, cooling by natural air is inadequate. In such cases, the transformer is located above the air chamber and a blast of compressed air is forced on core and the windings with the help of blowers or fans. This improves the heat dissipation, and hence higher specific loadings are allowed in dry type transformers. This reduces the size of transformers. The air supply must be properly filtered to prevent the accumulation of dust particles. Then comes oil natural, air natural, that is ONAN cooling of transformers. The transformer is immersed in oil, so heat is generated in the core and the windings is passed on to the oil by conduction. The heated oil transfers the heat to the tank wall, from where it is taken away to the surrounding air. The assembly of oil immersed transformer is shown in figure 4.30. The tubes are provided on the sides of a transformer tank. The oil in the tank is taken to the tubes. The circulation of oil through tubes causes the cooling. The temperature rise of a transformer can be reduced by increasing the area of heat dissipation. Number 2, decreasing the cooling coefficient. As the rating of the transformer increases, the plain walled tank cannot be used. It is necessary to reduce the cooling coefficient. This is achieved by some improved methods of cooling. The transformers up to 30 kVA use plain walled tanks, but transformer with ratings higher than 30 kVA uses corrugations, fins, tubes and radiator tanks. So, the figure 4.31 shows the tanks with the tubes and the external radiators. So, here are the tubes So, tubes provide the larger areas through which the heat can be radiated outside to the environment. The heat developed inside the transformer is taken outside with the help of oil. The oil is cooled with the help of fins, tubes or external radiations by natural circulation of air. Then comes oil natural air forced ONAF cooling of a transformer. In this method, the tank is made hollow and compressed air is blown into the hollow space to cool the transformer. The oil which is circulating inside takes away the heat to the tank walls. The method is effective and can be used for large rating transformers. Another way to force air blast is to use elliptical tubes separated from tank walls through which air is forced by fans. Oil forced air force, that is OFAF cooling of transformers. In the external heat exchanger, the compressed air is blasted with the help of fans to cool is the oil. The advantage of this method is at low loads, when losses are less, there is no need to use the fans to cool the oil. The natural air is sufficient. At higher loads, both fans and pump are switched on by sensing the temperature, which improves the cooling. Hence, the efficiency of this system is much higher when compared to the previous systems, and the schematic diagram is shown in the figure 4.32. So, this is your OFAF. Then comes oil forced water forced cooling of transformer. In this method, in the heat exchanger, instead of air blast, water blast is used to cool the oil. The pressure of oil is kept higher than the water, so oil never mixes with water in case of a leakage. Due to this method, smaller transformer size is sufficient, as it is not necessary to employ water tubes inside the transformer tank. The method is suitable for transformers having ratings more than 30 MVA. The method is employed for the transformers at hydroelectric power stations, as large water supply with appropriate water head is easily available. The schematic diagram of this OFWF is shown in the figure 4.33. Then we will move on to the protective devices and accessories. The following are the protective devices employed in transformers. Number 1 is conservator, breather, Buchholz relay and explosion vent. First of all, we will deal with the conservator. So, this is the schematic diagram of a conservator. Transformer conservator is considered as one of the most important transformer accessories. As the name implies, a transformer conservator conserves some amount of transformer insulating oil. By definition, the transformer conservator is an airtight metallic cylindrical drum which is fitted above the transformer main oil tank. A pipeline is provided to create a connection of transformer main tank and conservator, and this pipeline usually acts as a conservator tank which is partially filled with insulating oil. Oil is not allowed to come in contact with the atmospheric air, which may contain moisture. The moisture spoils the insulating properties of oil. The atmospheric air may cause acidity and sludging of oil. A conservator is an airtight metal drum placed above the level of the top of the tank and connected with it by a pipe. It is partially filled with oil. Breather. When the oil expands or contracts by the change in temperature, there is a displacement of air. When the transformer cools, the oil level goes down and the air is drawn in. This is known as breathing. The air coming in is passed through a device called breather for the purpose of extracting moisture. The breather consists of a small vessel which contains a drying agent like silica gel crystals impregnated with cobalt chloride. It removes the moisture from the incoming air. The silica gel is blue when dry and becomes pink when damp, that is moistured. Silica gel is checked regularly and dried up and replaced when necessary. Then finally, explosion vent. When there is an accidental internal short circuit in the transformer, an arc is struck between the turns of the winding. Due to this, enormous heat is generated by the arc and hence a very large volume of gas is produced. So, the pressure in the transformer tank increases dangerously high, which may lead to the explosion of the transformer tank. To avoid such accidents, an explosion vent is covered by a diaphragm of either glass or aluminum. When the pressure in the tank increases above a critical value, the diaphragm is blown out and release the high pressure gas into the atmosphere. The hot oil may splash and cause injury to the people nearby. So, for this reason the explosion vent is bent downwards. Buchholz relay. Buchholz relay is a special type of relay which is widely used for internal protection of transformers. This relay is mainly used in oil immersed transformer for providing protection against all types of internal faults like any insulation breakdown. By definition, Buchholz relay is an oil and gas actuated relay which is located in the pipeline connecting the transformer main tank and the conservator. Construction of Buchholz relay. It is a relay which is mainly connected in the pipeline between the main tank and the conservator, designed in the form of vessel filled with oil which is dome in shape. The device can be easily subdivided into two portions inside the vessel depending on its purpose and also its structure, that is the upper part and the lower part. So, before coming to conclude this session on transformers, we will have a quick recap of whatever we have studied. So, we have done the configurations, various configurations available in a transformer and the various parts of transformers, etc., and various applications, advantages and demerits of the various configurations, etc. Thank you.